All right, Prairie High School, welcome to Mays High School, third block class of 2018-2019. Thank you very much. So, physics. Let's get into it then. Here's the beauty of physics, is that unlike any science that you study, you all have an intuitive understanding of physics, okay? And you do. So here I've got an apple, right? So, got the apple here, I let go of it, what's going to happen? If I gave, here's the first quiz. I said, okay, class, here's your first physics quiz. Mr. Burkham is going to hold an apple and then he's going to let go of it. What's it going to do? It's going to fall, right? Why? It's gravity. Okay, great. So here's the first quiz. Everybody's going to get 100%, right? You're going to say, oh, it's going to fall because of gravity, right? Now, I also teach AP chemistry, right? And I guarantee you, if I walked in, most of you, I'm guessing, have had Chem 1. And if I said, okay, hey, let's talk about the carbon atom. Class, here's the first quiz on chemistry. How many electrons, and you've not studied chemistry. I said, okay, hey, how many electrons does a carbon atom have? And y'all would be going like, I don't know, okay? What's the structure of the electron arrangement of an aluminum atom? I don't know, okay? Y'all don't come in with an innate understanding of chemistry. Biology is even worse, okay? Because here's what everybody remembers out of biology. What is the role of the mitochondria? It's a powerhouse. It is the one thing everybody remembers about biology. Okay? What's the role of the mitochondria? It's the powerhouse of the cell. Boom, here you go. Okay? Everybody remembers that part of it. But you all don't walk in with an innate understanding. You know, if this was a biology class, and God forbid that I teach that. We'll talk about biology later. I have an aversion to biology. It's important, don't get me wrong, okay? But it's like smelly and gross, and I don't do that. And there's like an unwritten rule, don't talk biology in my room. So if like you feel the need to discuss something about like bodily functions, don't. I don't want to hear it, no one else does, okay? Go down to Miss Houseman's room, teaches AP biology. She likes that stuff, I don't. So no biology, okay? Just and it's like, what's wrong? No, just don't. Okay, so and if I said, okay, you're in a biology room, and I just gave you a picture of a cell and said, oh, here, find the nucleus. Okay, there, all right? You all wouldn't have an innate understanding. You all get physics. One of the Newton's second law of motion, which is this big sign hanging in the back of the room, it says F equals ma. We'll talk about that equation. And you all understand that equation. You've never seen it before, but you all understand that the F is the force, and then you have mass, and then you have acceleration. So you all, from a very young age, have probably learned that a big force equals pain, okay? If someone said, hey, I'm going to hit your hand with a hammer. No, don't, okay? You all have no concept of an equation, but you understand that if your hand gets hit with a hammer, that's going to hurt, okay? You get that. At a young age, you probably did not want to fall off the roof of the house. Even though you didn't understand gravity, you didn't understand acceleration, anything like that, you knew falling is bad, okay? You didn't understand, you were not born with an innate understanding that says, oh, aluminum is going to form a cation with a charge of 3 plus because it's going to lose its 3 outer valence electrons, leaving 13 protons pulling on the remaining 10 electrons, creating a smaller ion. No, okay? But you understand physics. So what my role is to basically get you to buy into this deal. To say, okay, what are we going to do in physics? So basically, what physics tries to do is that we're searching for a way to mathematically describe what is going to happen. That's the ultimate goal. So the other side of what I have to do as a teacher, and again, this is my 26th year of starting classes. And it sounds odd, but if you think about it, it's true. So before I taught at Mays, I was young and stupid and wanted to see the world. And so I joined the Peace Corps, and they sent me to Africa, and I taught there for 2.5 years, and then came back and started teaching here. Been here ever since. But in that entire time, 2.5 years in Africa, starting my 26th year here in Mays, I have never taught anyone anything. Okay? I never have. And you're all sitting there going, whoa, soft bus here. We call you teacher, and you're in front of the class, and you've never taught anyone anything. And I haven't. Because if you think about what happens in the learning process, I can stand up here and I can pontificate about black holes and Big Bang Theory and acceleration and all this stuff. and this information is going out. What has to happen for you guys, and this is more importantly, and this is what I see as I progress through the years, is that I've got to convince you guys to say, wow, this is cool. You guys have to put forth an effort from that side. Because if you don't, if you guys have checked out mentally, or you're not saying, man, this isn't worth the effort, then me standing up here and presenting the information doesn't do any good. I mean, I could stand up here and talk about, Shakespeare or biology, even worse, and it would be the same effect as y'all aren't going to learn it. So that's my job, is to present this information and get you guys to say, okay, hey, I'm going to take this information that Burkamp's putting out there, and I'm going to put forth the effort to learn it. I'm going to try and find a way to assimilate that information. So what I've got to do is basically, over 26 years of experience, perfected a way to hopefully get this in a way that you guys can understand it, where it's going to fit within your framework, and kind of how I sequence that deal out. But that's what I've got to do. That's the most important thing that I've got to do, is to find a way to get you guys to say, okay, hey, I'm going to put forth the effort. So if you look at availability, and it's like, let's say, for example, you're struggling with, okay, this doesn't apply, it somewhat applies to critical courage. So I'm here at 6:30 at the latest every morning. So if you're struggling with something, I'm here at 6:30. I don't have a life. I probably don't leave the school probably until 5, 6 o'clock in the evening. So, and there's encore, there's any number of things. So if you're reaching a roadblock, and hopefully you will, then come in, find me, get help. The worst thing that you can do, and I've had this happen, and it just drives me nuts. I've had this happen. I'm handing out the test. Okay, I'm handing out the test. And kids go, I really never did understand this unit. So okay, you're telling me this now. I'm handing out this, and you're just telling me, well, I really didn't understand this. Fantastic. Good. Okay? So if you reach a point where you're not understanding something, come in, we'll chit-chat, we'll find a way. Now, here's another thing. I have a little bit of passion when I teach about different things. And if you're here, and here's typically the sequence, okay? Jones comes in, she goes, with a little bit of attitude, because I know you, okay? She's going to go, Burkamp, I didn't understand number 4, because it's exactly how you would do it, isn't it? Isn't it? Don't lie, it's true. Okay, so she's going to come in and say, I don't understand. I'm going to go, Claude, this is going to be the sequence. I'm going to take the glasses off, okay? Put them down like that, and we're going to go, oh, come here, let's look at this, right? So if I do that, don't worry about it, okay? Don't take it personally. We're going to get through it, because I've got a little bit of passion about learning and about teaching and everything else like that. So if I get a little bit demonstrative when I'm helping you, it's okay, because if I didn't care, I wouldn't be willing to help you in the first place. So don't flip out if I throw down my glasses and I make a little noise when I hit the table, all right? So just so. All right. So here's the cool part about physics in terms of what we're going to study. So one of the things that, if you look like this rock that we're on, okay, that we call Earth, third one from the sun, okay, we're orbiting a very average star, okay. If you look at the billions of stars that exist in the universe, ours is very, very average, okay, which is good, okay. It's been around for a while. It's been burning for about 5 billion years, give or take about 10 minutes, roughly. And it should burn for about another 5 billion years. Eventually, the hydrogen is going to get used up because it's changing it all into helium. And it's going to die out, okay? And it's going to begin to expand and all that good stuff. Now, don't flip out and go, oh, God, we're all doomed. It's a long way away. Don't worry about it, okay? So, you got Mercury, doesn't have an atmosphere. Venus has an atmosphere, but it's an atmosphere on steroids, okay? Extremely high pressure because it's so thick and it traps all this heat. Don't vacation on Venus. It's not going to end well. So then you got this Earth, right? So if the Earth was an apple, imagine this thing cut in half. And you can see like this thin outer peel, this thin outer layer. On a relative scale, that thin outer layer is our atmosphere. That's what's allowing us to exist. It's just this thin layer on a relative scale. And we kind of have to have that atmosphere, because otherwise we don't have weather. Breathing is kind of a key component. It's kind of cool. But yes, breathing is a good thing. You know, and we have a magnetic field, and it keeps a bunch of these charged particles from impacting us and screwing up our DNA. And we've got a moon that creates tides, and we've got Jupiter and Saturn, these big gaseous planets on the outside that sweep up all these asteroids that can impact us. And so, as we develop the ability to find exoplanets, meaning planets outside of our own solar system, we thought we should find a lot of planets like Earth, okay? Well, here's the weird thing. Even if you look at like all of the planets we found, none of them have like a typical characteristic like the Earth. They're either really, really big, or they're really small, or there's a whole bunch of things. Like, of all the planets that we've looked at so far, we're like the unique one. Okay, so we're kind of the strange rock out of everything that we have found. And so that's the cool part about physics. People ask me, like, what do you do? They said, teach physics. They go, oh, that's boring. I was like, oh, for the love of God. Okay, physics is the coolest thing on earth. And here's why. Because if you look at the span of what physics covers. So, anybody ever heard of the Jet Propulsion Lab, JPL? What does it do?
Not sure.
Okay, JPL basically launches rockets to Mars. They're in charge of like the probes to Mars and stuff like that. Okay, they're a branch of NASA. Okay, they do cool things. And so, like last year in September, if you paid attention, there was the Cassini spacecraft that we crashed into the surface of Saturn. Spent all this time orbiting, went through the rings of Saturn. One of my former students, Michael Stoffel, took physics in this room, and he was like the mission director for that spacecraft. Like, he was the one that hit the button that sent the signal to the Cassini spacecraft to tell it to crash into the surface. And so he came back and he was visiting here. And he says, "Hey, come out to JPL and I'll give you the inside tour." So at this point, this is like physics teaching nirvana, because okay, great. Here's a former student that's at JPL and can give me the inside tour. It was like, oh my God, I must go. So we've got one branch of physics that's dealing with like the extreme. It's like, okay, what's the mass of the sun? How are we going to figure that out? Well, what's the diameter of the Milky Way galaxy? How are we going to get, a probe to land on Enceladus, one of the moons of Saturn? So you've got one branch of physics that is dealing with this extreme of distances and extremes of mass. Now, the other side of physics is what another one of my former students was doing last summer at Fermilab in Chicago. Fermilab was the first big particle accelerator that existed in the United States. And so the Fermilab is dealing with particles that are extremely small. Like, what are protons made of? What are neutrons made of? Right now they're dealing a lot of stuff with what particles called neutrinos. So neutrinos are these extremely weird particles. So if you consider your pinky, and the end of your pinky is roughly like 1 centimeter by 1 centimeter, and don't flip out and go, oh, this is weird. Okay, there's other things that are weird. But basically about every second that goes by, about 1 million neutrinos pass through the end of your pinky. Okay? It's like, whoa, I feel them. Wow. Okay? No, you don't. Right? They've been going through you since you were born. Don't flip out. And so what we're trying to figure out is that, okay, how are these particles that are so abundant in the universe, but they basically have absolutely no mass, they pass through us, they don't interact with anything, but yet we got to kind of figure them out, because there's a couple of things that are rather embarrassing in the field of physics right now. One being this concept of dark matter. Okay? Dark matter makes up roughly, depending on which book you look at, 70 to 80% of the universe. Okay? So there's a big mass of our universe that's missing. We call it dark matter because it doesn't interact. We know it's there, but we can't find it. And so that's pretty embarrassing. It's like, hold on, we're missing 70% of the universe, and we think we're intelligent. Wow, cool. No. And then you get into dark energy, because dark energy is something else, because it's making the universe accelerate faster than it should. So we got some things that aren't quite right, and we got to kind of rework some things. So here's where neutrinos play into this story. If you subscribe to the Big Bang Theory, Big Bang Theory states that basically there was an event called singularity. All of us, everything in the universe was condensed into one infinitely small point. Something happened, they pulled the cork on it, whatever, and it began to expand. But it started off as pure energy. And then it began to cool down, and as it cooled down, it began to create mass out of that energy. And so here's the analogy. What's the square root of 4? 2, or negative 2. Okay, there's two possible roots. So when particles form, like let's say for example electrons, most of you have been through Chem 1. What charge does an electron have? Negative. Protons have a positive. In our normal universe, that's the situation. So electrons are negatively charged, protons are positively charged. But what we found is that there's antimatter. Antimatter is weird because you have electrons that have the exact same mass, but instead of being negatively charged, they're positively charged. So we call them positrons. And then the protons, instead of being positively charged, they're negatively charged. But here's where this goes south, is that when matter was beginning to form, what should have happened, theoretically, is that you would produce equal amounts of normal matter that we have and equal amounts of antimatter. So it's like taking the square root of 4, positive 2, negative 2. But what happens is that whenever matter and antimatter collide, they revert back into pure energy. So if there were always equal amounts of matter and antimatter being created, we would not be here having this discussion. Because whenever you formed matter, it would automatically collide with the antimatter particle, it would annihilate itself, and it would go back into pure energy. So what we've got to figure out is that what tipped the scale? Why did the universe create more matter and not as much antimatter? And they think neutrinos are going to be kind of the key to solving that riddle. And so that's why the Fermilab is doing so much research with that. So Reed Bowles, he was up there doing his internship last summer. He called me and says, "Hey, I got an internship at Fermilab. Come up, I'll give you the inside tour." It's like, oh my God. So road trip to Chicago. So I have two former students that are working in the extremes of physics. One is, sending probes to, Saturn and going the rings of that and talking about, the size of the universe. And then I had another former student that's working and trying to figure out, okay, what are protons made of? What are neutrons made of? How do we explain the existence of neutrinos? So that's the beauty of physics, is that it spans such a great expanse in terms of what we're going to study. So we're going to kind of, to a certain extent, deal with the medium in between those two. Kind of like your everyday life, what do we got going on? Okay, I dropped the apple, boom, it falls. All right. So there's also like a couple of themes that we will develop through the year. The first one, and I've had these epiphanal moments throughout the years, is that Mother Nature is a lazy prima donna. Okay, and you sit there going, what does that even mean? So here's the deal. Mother Nature is only going to do what is easiest for Mother Nature. Okay, that's it. That's what Mother Nature is going to do. So right now my room is actually relatively clean. Trust me, it's going to get dirtier. It's just really not my thing. I got other things to worry about. But let's say, for example, that I can't find, I don't know, a binder clip that should be on my desk. Okay, so I can look one of two places. I can look on top of this bowling ball, and by the way, this bowling ball is actually like Hank, and it says Hank. Okay, Hank's going to be a key part of a lot of stories. So class, Hank, this is the class. So when you hear me talk about Hank, this is what we're talking about. And here's the odd thing: I have no idea how this bowling ball came to be in my room. I came back from summer vacation, and this bowling ball is here. I don't know how it got here, and literally it says Hank across it. Okay, so I'm not like, I didn't randomly start calling the bowling ball Hank, but that's who we're stuck with. So I could look in one of two places, and allowing for the fact that this paper clip is just bopping around. What are the odds, or where would you think I would most likely to find this paper clip? On top of Hank, or in the bottom of this sink that's up here? Where do you think it's going to end up most likely? Bottom of the sink. Why?
Because it can't fly.
Because it can't fly. Mother Nature is a lazy prima donna. Mother Nature is not going to go, I'll mess with Burkham. I'll lift this up and I'll put it on top of Hank. No, Mother Nature is going to go, that was simple. I'm going to take it to the lowest possible energy level. That's what Mother Nature does. Mother Nature is lazy. Mother Nature is not going to do anything that it doesn't have to do. So if you begin to look at the events of a universe, and if you keep that in mind, you begin to see trends. Now, the other thing that we'll talk about, and this will make sense in just a second, and over here, Sean Engler drew this, it's called Jedi Stoffel. Okay? And the Stoffel law stands for stop the force and watch. So we'll spend a lot of time talking about that. So because here's where these two ideas merge together. So Mother Nature is a lazy prima donna, and you stop the force and you watch. So this apple, when I let go of it, you all know, oh, it's going to fall. But here's the deal. Mother Nature actually doesn't want to make this apple fall, because that means it's going to accelerate. That means it's going to change its velocity vector. So we'll spend a lot of time talking about vectors. So the short version of vectors that you all just need to know for now is that when you're moving, you have a vector that defines your direction and how fast you're going. So like, let's say you leave here and you're going to drive south on 119th. Okay, so your vector is pointing south on 119th Street. Okay, and the faster you go, the bigger the vector becomes. Okay, so you're going from 5 to 10 to 15. Okay, none of you would ever speed. High school students never speed. So you're going to hit exactly 55 miles an hour, and you're going to put it on cruise control, and you're not going to do anything stupid, and you're not going to go over that. Okay, so then you're going to go, okay, 55, cruise control, boom, here we go, because I'm a teenager, boom, this is what we're doing, we're going to go south. Okay, so once you establish that vector, that's what Mother Nature wants to keep. Okay, so if that vector ever changes, you speed up, you slow down, you turn. So if that vector ever changes, that requires a force. Okay? So we'll spend an entire day talking about that, but that's the basic idea. So the idea is that Mother Nature does not want to create or change any velocity vector. And to do so requires a force. So when I let go of that apple, the apple actually wants to stay there because it doesn't have a velocity vector. Well, as soon as I let go of it, and I observe that it begins to accelerate, then I realize, oh, there has to be a force acting on it, because that apple does not want to fall. The apple is at rest. The apple goes, hey, I'm kind of cool here. Got a nice view, you know, kind of floating around. Ooh, look at me, okay? And all of a sudden, that's going to fall, right? So that tells me that there's a force acting on it. So if I take that same apple and I roll it, what's it going to do? Every time, what is that apple going to do? Well, assuming it doesn't fall, but on the table, what's it going to do?
It's going to stop.
It's going to stop. It's going to come to rest. I can do this all day. Here, class, here's another example. We'll roll it again. Guess what it's going to do? It's going to stop. Okay? So, but it doesn't want to stop. It actually wants to keep going. And so by virtue of the fact that it stops, I realize that there has to be a force acting on it. So when you make these observations in a physical situation, so if you keep this idea in mind that Mother Nature is lazy, and if you stop the force and watch what happens, and if it accelerates, you know that there has to be a force acting on it. So one of the words that I forbid you to use in this class is the word decelerate, okay? Because all it's going to do is confuse you. So if you look at Newton's second law says force equals mass times acceleration. There is no force equals mass times deceleration. Now, it's not, okay? You will never see it F equals md. It's always F equals ma. So in the context of this class, when I say the word accelerate, and I'm going to say it a lot, all I'm talking about is changing that velocity vector, making that velocity vector bigger, and you're going to speed up. If I say your acceleration could also make you slow down, and you're going to hit the brakes, because then you're going to make that velocity vector smaller, or you're going to turn your steering wheel, and you're going to change the direction of your velocity vector. So today, on your way home, you can go, you can hit the brakes and be, whoa, look, I'm accelerating. And people go, no, you're not, you're decelerating. No, you're accelerating. And so the reason I don't want you to use the word decelerate, because it's just going to get confusing for us. Okay? So that way, if I'm saying acceleration, I'm not necessarily talking about speeding up. It might be slowing down, it might be turning. Okay? So get out of your minds now that acceleration is speeding up and deceleration is slowing down. If I'm talking about acceleration, it might be speeding up, it might be slowing down, it might be traveling in a circle. Okay? So let's just kind of get that straight. Okay, Max, stop that for a second. I know y'all read this. Party started back up again. Okay. So on the odds and end things in terms of like bookkeeping, here's how I'm going to determine your grade. Homework is going to be 25%, labs are 25%, tests are 50%, and then at the end of like the term, you're going to have like a written final, and then at the end of the class, you're going to have like a lab final and another written final. So if you're really worried about how you grade things, that's what's going to happen. In terms of what you need to bring each day, get a calculator, okay? You don't have to buy the TI-85 Platinum solar powered, whatever, okay? Whatever, okay? Just a good scientific calculator. Now, obviously, don't sit there and go, oh, I'll just use my phone. No, okay? That's not an option, right? And especially on tests, like, I'll just get my phone and I'll use it on the test. No, okay? So, get a calculator, because basically, at the end of the day, I teach a math class, but I get to blow stuff up, okay? Literally, that's what physics is. Because when I went through K-State, my primary emphasis was actually mathematics. Like, I did Calc 1, 2, 3, differential equations, all this weird math, okay? But then I figured out that teaching math is, quite frankly, pretty boring. Okay, it's important, but it's boring to teach from my perspective. And then I thought, wow, there's physics and chemistry. I can teach math, but I get to have like roller coasters and like beds of nails and, you know, helicopters. So I can go to the principal and go, hey, Dr. Potts, I need a small remote control helicopter. Why? Oh, I'm teaching forces. Okay, yeah, here, go buy a helicopter, you know. If I'm teaching math, I go to him, it's like, you don't need a helicopter. So it's like, here, have a calculator. Okay, so we're going to do a lot of math, but it's going to have like meaning to it. And I'm not saying that math isn't important. You all have to have math, but this is just going to be math, where we get to, you know, blow stuff up. So it's kind of a cool deal. As far as like a notebook goes, I'd recommend it. I'm not going to worry about it. I'm not going to go through and check that you've kept your notes and everything else organized. I have other things to worry about in my life, and whether or not you keep a notebook, you all are big people, that is up to you. I'm not going to worry about it, okay? I know you all just got like the Chromebooks, okay? We will never use them in this class. So, because I'm old school and I make you write out everything, so I can't imagine the really need to bring Chromebooks, at least as of right now. So, if that changes, I'll let you know, but as of right now, don't worry about bringing the Chromebook because we're not going to use it. Let me see. That covers about everything. Well, there's going to be more stuff that we'll talk about later, but that's kind of the nuts and bolts in terms of bookkeeping. Pretty Prairie, this won't apply to you, but this is something I got to go over with you guys here on this first day. In case, and it's sad that I've seen this change in 25 years, that we have to even talk about this. So, in the case that there is an active shooter, okay, and it pains me that we've gotten to this point that I have to talk about this as a teacher. This isn't a bad room to be in, and I'll tell you why, because like I've got 2 rooms back there that's capable of holding the classes. I've got a bed of nails back there, which we'll talk about later. We've got mass sets with like 1 kilogram masses that throwing at someone and hits them will completely like knock them out. I've got any number of bottles of like concentrated hydrochloric acid back there. So if something happens, hey, you know, we're okay. And if you're in an English classroom, what are you going to do? Hide behind my book, okay? No, right? So we got that advantage. And there's like any number of ways out of this room, okay? You know, we can go through that door over there, you know, and then we can make our way back through that. So that's kind of, if we have to hunker down, we'll hunker down in here, we'll deal with that. If we have to like do the run thing, cross the way, cross on the south side of 45th Street, there's a housing development, make a break for there, you know, I'll hold up a sign or something, hey, all the physics nerds gather here, okay, so when you see the physics nerds all getting together, that's where you need to huddle up. If there's a fire, here's a short version, go out this door, take a left, hit the fish tank, take a right, okay? Simple way to get out of here. If there's a tornado, we'll go down to the Mace Career Academy, and it's odd, we're going to be like out in the hallway. I took that person, it's like, we don't get to be in the room. No, you have to be out in the hallway. It's like, really? That's kind of rude, but they said it was fine. Okay, whatever. I've lived in Kansas, like, except for 2.5 years in Africa, I've lived here all my life. I've never even seen a tornado. So, statistically, you know. Pretty Prairie, that doesn't apply to you. You do whatever you need to do. You guys are on your own at that point. Okay, well, it's true. I mean, nothing personal. All right, let me see, got through that. Now, here's the other thing to talk about, and that's like, why would you study physics? Like, why beat yourself up? Why do you suggest that, you know, why are you going through this, and why do I suggest that you stay in here? the job market that you guys are going to be going into is going to be different than any other generation has ever had to like experience, in the sense that because of the development of artificial intelligence, it used to be you could walk out of Mays High and go get a job, you know, at a factory or, you know, a decent job there, or like at a warehouse, being in charge of inventory, you know, that type of thing. And they were, you know, you weren't going to get rich, but you know, you could make a decent living at it, okay? And that was an option, okay? Well, guess what's happening to a lot of those jobs? They're gone, okay? They are being replaced by computers that can do them much faster, much cheaper. The computer isn't going to, you know, call the boss and go, you know, I had a fight with my boyfriend, I'm not coming in today, you know, sorry. Or, you know, the computer isn't going to stop and check their phone. Oh, I got a text from my, you know, girlfriend and I got to go home. She's upset because her cat has a fur ball. You know, I don't know, okay? So that's just the reality of it. Even if you look at like UPS, okay, or, you know, I'm guessing most of you at some point have ordered something from Amazon, and most people have. And, oh, that gets loaded up on a UPS truck, and the driver comes and drops it off at the door and goes back. And he makes a decent salary, 20, 25 bucks an hour, okay, not a lot of stress. Hey, you drive around, you drop off packages, not bad. Well, guess what Amazon is looking at? Amazon is looking at using drones. What's going to happen to those $20 to $25 an hour jobs? They're gone, okay? They're gone. Look at Uber, okay? Uber is very actively pursuing right now driverless cars. And we'll say, oh, I'll get a job working as a driver for Uber. Well, guess what? That job is going to be gone. So the advantage of studying physics is that you guys are going to be going into a very competitive job market. Now, even though I've taught this class for like 25 years, I promise you, you will probably never be walking down the street and someone's going to walk up to you and go, oh my God, it's a life or death situation. I need to find the final velocity of this marble when it's dropped from a building 5 meters high with an initial velocity of 2 meters per second. Do this or the world is going to end. No, okay? It is not going to happen. But what is going to happen, and then this is what you're going to learn, is that you're going to learn to think through very, very complex problems. And that's something that, in terms of you getting ahead financially, socially, however you want to view that, that's a vital skill that you have to have. Because I promise you, no one is going to pay you $80,000 a year to sit in a cubicle and add numbers together. It is not going to happen, okay? And if it's a mundane job, that job is going to be replaced by a computer that can do it faster and cheaper. So what you have to have is a unique set of skills that says, hey, this is what I can do. If you look at your graduating class, pretty small percentage take physics. Right away, that gives you a leg up in terms of like, wow, okay, here's a competitive job. I've been through physics. I can solve these complex problems. Okay? I'm not guaranteeing it's like, oh, I took physics. I'll be a millionaire by the time I'm 30. No. Okay? Wish it was that simple. I really do. But it's going to teach you how to think. Now, like I talked about before, it's hard work. So there's a couple of promises that I will make to you. Okay? I will never, ever, ever give you busy work. Okay? I'm not going to do it. Okay? I hated it when I was a student, and you all, you all have been in this education gig for a while. You all have pretty good busy work detectors. Okay? And you kind of get this sense like, this busy work. And everybody rolls their eyes and they hate it because there's no educational value to it. So I promise you, whatever I give you isn't just busy work. Now, here's the other thing. We will never, like on an assignment, so here's typically how a day will play out. Our beginning of the class, we're going to go over yesterday's assignment. And I'll say, hey, does anybody have any questions, right? So let's say, I don't know how to do number 5. All right, fine. And here's the other thing. If you don't know how to do number 5, there's 24 people in this class. I'm guessing there's probably 7 or 8 people that also don't know how to do number 5. And those other 7 or 8 people are going, thank God somebody asked, because I didn't know how to do it either. So I guarantee you, if you don't know how to do a problem, odds are there's a whole bunch of other people that don't know how to do that problem either. And even if you just say, hey, can you give me an idea of what the answer is? And I'll do that. Like if you say, hey, roughly what's the answer to number 5? And I'll say, okay, hey, it's somewhere between like 10 and 14. So I might not tell you the exact answer, but I'm going to tell you kind of a range. If you say, hey, I have no idea how to work this problem. Okay, right, let's work through it. So that's how that'll play out. And say, okay, hey, class, hand in your papers, all right, hand in your papers, all that good stuff. And then we're going to start like the next topic, do a lab, something like that. And then you're going to have some time to work at the end. So that's typically how a day will play out. We'll cover the concepts, we'll learn that, then we'll do like an application, do the lab part of it. Okay, and that's the cool part of physics. Oh, hey, we learned this. All right, hey, let's go look at a lab situation. So that's typically how a day is going to play out in the life of this class. So when you look at how that's going, to train you and how to solve complex problems, that's a bio skill that you're going to have. So when I look at the amount of work that I'm going to give you and why this is so important that you do this homework, here's the other promise that I'm going to make to you. 99% of the time when you hand in an assignment, I'm going to get it back to you the next day. Because I don't have a life outside of school. I'll typically spend 2 or 3 hours a night grading papers. Okay, that's kind of what I do. And people go, why? It's like, and kids say, here's the classic thing that you all will say. And you all think you're clever and you think you're the first people, of students of mine, to make this observation. And you'll go, Mr. Burkett, if you didn't assign homework, you wouldn't have to grade it. Really? I had never thought about that. Dear Lord. Okay, so here's the deal. If I thought you all could learn physics without me assigning homework, and I could just stand up here and pontificate and say, oh, here's this equation, v squared equals v naught squared plus 2ax. Here's your initial velocity, here's your final, here's your distance, boom, here you go. All right, let's move on. And if I thought you all could learn it that way, I'd do it. Like, I'm not some kind of like masochist where, wow, I just have to grade papers for 3 hours a night to give meaning to my life, okay? No, okay? This is the other promise. If I'm not going to give you busy work, it's going to have meaning to it. And with this class, like, I'm not going to give you all textbooks. Everything that you're going to do, every lab, every homework assignment, the test, the lecture notes, is stuff that I have written over the years. Because that way I can integrate it, and we're going to start here, and we're going to build, and then that's going to build onto the next assignment, and that's going to build on the next assignment, and that's going to build onto the next lab. So that's the beauty of me, basically being able to write all this stuff, because I know what's going to happen. I can kind of see like the light at that end of the tunnel. Say, okay, where are we going to end up? And so, when I give you assignments, I'm going to grade it, and it's going to have meaning. I promise you. I'm not going to give you assignments just to fill up time. It's a waste of your time, and it's a waste of my time. So if I'm going to take the time to grade it, it's going to have some meaning to it. Okay? Because that's kind of, it's hard work, but welcome to reality. If you're going to be successful, 99% of the time, people that are successful just work harder. They might not be smarter, but they work harder. That's the reality of it, and it comes down to a work ethic. And so hopefully, you realize this. So there's that. Okay. Any questions so far? We're good? So the first unit that we're going to go over is what's called the mathematical toolkit. So to do physics, there's a process that you have to do. Okay? What are we going to measure things? How are we going to do this? So the first unit is somewhat analogous to being a mechanic. So let's say that Shively's car, it's not starting. He gets it down to the mechanic looks at it, and he goes, okay, hey, Shively, your alternator is out. So for those of you that don't know what the alternator does on your car, your alternator spins and it recharges your battery. Because every time you start your car, that drains electricity from the battery, and that electricity has to be put back, and that's the role of the alternator. Okay? So there's your quick lesson for the day. So mechanic goes, hey, your alternator is out. Well, if the mechanic only knows that the alternator is out, and that's the extent of it, well, that's cool. Okay, nice. And then Shively goes, well, can you fix it? Oh, well, no, I don't have any tools. Okay, great. What good is knowing that the alternator is out if you can't fix it? So the same thing is true with dropping this apple. If I drop this apple, and you all know it's going to fall. Why? Oh, because of gravity. What's it going to do? It's going to accelerate. Okay, cool. That's like saying the alternator is out. So what we've got to figure out is that what can we measure in terms of the apple falling? Okay, hey, we can find the mass of the apple. We can figure out how far it falls. We can figure out how long it takes. Because ultimately, what the role of physics is, we're trying to find a way to describe mathematically what happens in the universe. That's the role of physics, okay? We're trying to find a way to do this. So like, let's say for example, we come up with an equation and we say, okay, I dropped this apple and the equation says it should take a half a second, okay? And then we drop the apple and we measure it and it's about a half a second. Okay, hey, the equation is valid. But if I come up with a different equation that predicts that it should take like 5 seconds, and I drop the apple, and it's not anywhere near 5 seconds, well, that equation isn't valid because it's not describing what's happening in physical reality. So that's basically what physics is all about. Y'all want to get an equation sheet, oddly enough, with a bunch of equations on it. I know you'll find that shocking. That's why we call it an equation sheet. And you'll have that, and we can go through it. And all these equations are basically there to allow us to describe mathematically what is happening. How long is it going to take for the apple to fall? You know, that's what we're after. So, stop that again. I'm going to hand out selection notes. Okay, so when you look at physics and what we measure and all this good stuff, so one of the things that we had to decide was what units are we going to use to measure stuff in, okay? Are we going to work in inches? Are we going to work in centimeters? Are we going to work in meters? How are we going to measure time? Are we going to measure it in hours? You know, what are we going to do? So they got together and had a conference with pizza and whatever, and they said, okay, we're going to work off the MKS system. Okay? The MKS stands for meters, kilograms, and seconds. So those are like the 3 fundamental units. So here's the beauty of physics, is that what we talk about today with this MKS system, it isn't like we're going to cover it today and then we're never going to talk about it again the rest of the year. Okay? Everything that we talk about today with this MKS system, and then tomorrow we're going to use that to develop velocity and acceleration and force. So those are going to be the first 6 units that we develop. Literally, up until probably the middle of October, everything that we study is going to be measured in one of those 6 things. Meters, kilograms, seconds, then you can have velocity, which is meters per second. You can have acceleration, which is meters per second squared. You can have force, which is kilograms meters per second squared. So literally, these first 6 units that we will use everything until we get to energy, which is measured in joules, and that's still a combination of these letters. So this is like the basics of what we're going to do. So you can come up with the best equation in the world, but you have to be able to measure this. So it said, okay, what can we measure? Okay, we can measure distance. Okay, that's cool. Not a big deal. Here's meters, right? Meter stick is about yay long, kind of give you some reference, right? And we have smaller divisions, centimeters, that type of thing. You all will not struggle with that concept. Time, not a big deal. Seconds, okay, that's kind of cool. Time is pretty much a constant in our world. It gets weird, like if you go close to the speed of light, time actually slows down, okay? But that's Einstein's theory of relativity. Don't worry about it, okay? Like technically, like when you stand, when we're standing here on this spinning rock, my head is actually going faster than my feet is because it's like a marching band. Have you ever seen like a marching band and the people here move slow, you know, you're moving around in a line, the people here move slower than the people on the outside. So when you stand up, technically your head is going a little bit faster than your feet are because it's farther from the center of the earth. So don't then go, oh, I feel that. No, you don't, okay? But, so technically time is, in your head, is different than it is at your feet because your head's going a little bit faster. Now, don't think about that too much or bad things are going to happen. No, it's true, especially when you get into like the world of the electron, okay? Like particles, that type of thing. And this is the honest God's true story. If you think about what happens on an atomic world, you'll do drugs. I'm not making this up. Because it gets so weird. No, literally, if anyone says that they really understand what's happening in the world of the atom, probably not. Because here's the reality. Like when you, quote, touch this table, you don't actually touch it. You've actually never touched anything in your entire life because you have a repulsion of these electron clouds at an atomic level. But you're going, look, working up, you are pounding on the table, okay? You are making noise, right? I am. But an atomic level, and it boils down to what do you define as touch? Okay, well, if you shrink, and you can shrink down and you can look at what's happening on an atomic level on your hands, okay, you have a nucleus, which is extremely dense, and then you have this electron cloud. So like on a relative scale, if you imagine like a football field, the nucleus of any atom is like a cantaloupe on the 50-yard line. The rest of the stadium is the electron cloud. Those where the electrons are. And so when you imagine like two football fields together, okay, on that size, the two nuclei are never going to touch. You're going to have repulsion caused by those electron clouds. And you go, oh, that's deep, okay? It is. And so there's a whole bunch of weird things that happen on atomic level. And it's a good thing. Atoms are stable. Like the tables that you all are sitting at, except for the ones over here, those tables were bought in the fall of 1994. Okay, back when Mays High School was over there on what's the middle school? Mays Middle. Okay, that was when I started. That was the high school, and those tables were over there, and now they're here. And so when I come back after summer break or in the morning, there's a lot of things that I worry about. These tables have been tables for a long time. Okay. The atoms are pretty stable, right? And it isn't like I walk in and all of a sudden my tables have turned into like squirrels, This would be really weird because that would be biology, that would be even worse. And it's like, what happened to your tables? I don't know, but there's a room full of squirrels. So at that point I quit. Anyway, so atoms are stable, and that's a cool thing, right? Because if they weren't, then we wouldn't be here having this discussion. And so when you look at what we can measure and what we can study, okay, one of the things we'll talk about is mass. All right, well, mass is created by these atoms, which are made up of protons, electrons, and neutrons. And so when I let go of this apple, it falls because every proton, electron, and neutron that make up this apple is attracted to every proton, electron, and neutron on this big rock that we're sitting on. And so when you talk about mass, mass is just how much stuff there is in the apple. If I take this same apple to the moon, am I going to change the amount of stuff? No. So the mass of this apple is not going to change. Now, I drop it, and that's a measure of weight. Weight changes. It weighs less on the moon because even though I have the same apple, the moon doesn't have as much stuff. So there isn't as much stuff for the apple to interact with on the moon. Therefore, it weighs less. I drop the apple, it would be like watching it fall in slow motion. It's still attracted to the moon, it's just not going to fall as quickly. On Earth, okay, that's a pretty good acceleration because this is interacting with all of this matter that makes up the Earth. So, one of the things that I want you to get straight is this difference between mass and weight. You all are used to thinking as weight as being in pounds, okay? It's like, hey, what do you weigh? 150 pounds. Okay, cool. When I'm talking about weight in the physics class, that's going to be a measure of an attractive force, and we'll talk about this later, tomorrow, as a matter of fact. It's going to be measured in something we call newtons, okay, named after Isaac Newton, go figure, okay? Thank God his last name wasn't weird like, I don't know, but Woloski or Woloski, I don't know, Woloski, like, wow, what does it weigh? We're going to measure weight in Woloskis. Lord, seriously. Okay, so at least it was something simple. And no, fig Newtons were not named after Isaac Newton. Okay, let's just get that straight right now. So, oh yeah, fig Newtons. No, completely different. So, okay, let's call it a day. So here's your quote homework, is to read through those lecture notes. So tomorrow I'm going to come in and talk about derived units. We'll do the first lab tomorrow. You've been a wonderful studio audience, and we'll continue this tomorrow.